Hello, welcome to the next lesson on projectile motions with resistance. So in the last lesson, we introduced the concept where we compared projectiles with resistance to the 3-unit extension 1 projectiles where they don't have resistance, it's only gravity at play. So as you saw, the algebra and the integration was a little bit intense, but nothing compared to what we're going to do today, where we're still going to do resistance on projectiles, but we assumed last time that the resistance was proportional to velocity, while in this lesson, we're going to assume resistance is proportional to velocity squared. So just a heads up for the next lesson, the final lesson in this 3-part series, I'm basically going to bring everything together and hopefully do some past paper questions on resistance with projectiles. So just to be clear, I mean, this is the first year of the new syllabus, so there's not a lot of past papers out there with these types of questions, but I did manage to find a few, so we'll be doing some of those next lesson. So without further ado, let's hit up the slides. All right. So obviously a very good starting point is to look at the formulas that we had last lesson. So you can see on the left there, no resistance. That's the classic sort of 6 equations of motion from extension 1. Last lesson, we basically assumed resistance is proportional with velocity and derived these formulae using these initial conditions. So a very logical point to start is under section 2, part I, so we're going to go on to part 2I, where we assume resistance is proportional to velocity squared. So let's start there. So part 2I, resistance proportional to velocity squared. Obviously, better English would be square root of velocity, but yeah. Now, the diagram itself is actually very similar, but just to exaggerate the point, it's probably gonna look like a much smaller projection range than the other two, because we would expect that if it's proportional to velocity squared, the resistance is going to be a much more powerful element at play. So we're still going to assume initial velocity of u at theta degrees against the horizontal. And the diagram itself is exactly the same as previously, where resistance on the x is against range of motion, direction of motion, and so is the y. And we have gravity. So let's just put gravity at play here. So just like what we did last lesson in a good cooking show, I've prepared the formulas in advance. Down here, you can see that the formulae themselves are much more involved, especially on the vertical. So let's prove these now. A logical point also to copy in is to have the initial conditions in there, because we're going to assume the same initial conditions starting at the origin with the decomposition of the u vector as well. So, and that's obviously to help us integrate. So without further ado, then let's hop in to horizontal and see if we can prove these formulae. So I'm just going to, like I did last week, copy in the formulas into the left and leave those there. And this is what I'm aiming to prove. All right, so the given acceleration on the x is minus k v squared, where k obviously is a constant. So we start there. We obviously replace acceleration because we want velocity and displacement with a dv dt, and that gives us a starting point for this process. We're going to use differential equations where we take the v's on the same side and maybe throw the dt over with the k, and you get an expression where it's 1 on v squared dv minus k dt, and then integrate both sides. Nothing too fancy there. So that obviously gives us -1 on v. If you're a gun at integration, do that in one step, and this side minus kt plus our first constant. using our initial conditions when t equals 0. Initial velocity on the x is u cos. So that guy's 0. Subbing u cos into here, you sort of get like your first constant to be negative 1 on u cos. So nothing too wow about that. You can then see that if I was to sub this guy into C1, all of the values are negative, which is fine. I just will then make them into positives by multiplying it by -1. All right, so make this guy positive, positive, positive. Now, what am I after? I'm after velocity here. I need to make this guy the subject, so smart thing to do, common denominator this side, and then sort of reciprocal both sides. Yeah. So 1 on v equals to common denominator of that of u cos, times that up. Now I'll put the t on the back because that's the variable. So I'll just put cos over here, t plus 1. Reciprocal, you can sort of see that's exactly what that expression is. So done. Just scroll down slightly. U cos theta with a k in front. T plus 1 all over u cos. Beauty. All right. 2 down. 4 to go, right? 2 of the horizontals done. 1 more. So now I need to integrate this guy again to get the displacement expression. So what I'm going to do, like I always do, I'm just going to borrow this expression, and I'll just paste this up here. Remove the stuff I don't need. All right. Let us copy this up and do a bit of a zoom in. All right. So we start with this again. We replace that with dx dt. And then my aim here, it looks complicated, right? Just because there's a lot of stuff, but actually it's not too bad. Oh, did I not? I didn't even reciprocate. What a clown. So what I'm going to do, I said I would do it, but I actually didn't end up doing it. So that was very silly of me because the expression needs me to reciprocate, right? So let me quickly fix that little boo-boo. Cos theta t plus 1, and I need to copy this guy up here. And it's this expression that I need to replace with a dx dt. And what I was saying just then was the right-hand side looks a bit complicated. There's a lot of variables in play, but what you end up seeing or using at the end is it's just a linear expression downstairs. Everything else is constant. And what that means is when I integrate, when I integrate both sides and throw the dt over, it is just an ln expression. So what I need, so obviously integrate dx, that's just x. For this side, now the derivative of the thing in front of t is that, so it's just missing the k expression here. So I'm just going to multiply that by k and then 1 on k in front. And then that's my ln. So it becomes 1 on k ln of the denominator function plus 1 and then plus my second variable. Let's have a quick look. It almost looks like the thing I need to prove. So I'm hoping in this case that the C2 is 0. So when my initial conditions t equals 0, I know that x equals 0. So when that's 0, ln 1 is 0, perfect. And I can conclude that C2 is 0, therefore get my final expression for displacement horizontally to be this. It's not too bad. Yeah, not too bad. Vertical is going to be much worse. So just giving you a bit of warning before we do that. So that's horizontal, not too bad. Let's copy this for the vertical. But not only that, I want to uncrop that bit. Let's get that bit back in. And we focus on the vertical. And let's go there. So here we go. Hold on to your seats, all right? This is going to be a bit of a bumpy ride. So we start with the acceleration on the y being minus g minus k y, v squared, or yeah, mostly. Now the reason why this one's a bit of a bumpy ride is because that minus g doesn't allow me to just divide this over and then just do what I did before. It just makes integration a bit more painful. So I'm just going to replace this with dv dt. And you can imagine when I divide this using differential equations, I'm going to get a v squared here. So it's probably going, with a constant here, is probably going to look like tan inverse when I integrate. So maybe it's worthwhile factorizing the negative k out, or force factorizing the negative k out, where it's like taking out the negative k from that, I'll get g on k plus v squared. So it's a bit of planning for the future. So when I use my differential equations, these guys go on the same side. The dt and the minus k go on the same side. So I have an expression that sort of looks like this, ready for me to integrate. That's minus k dt. Let's integrate both sides. Now let's see where this takes us. It looks completely messy because of tan inverse, and that's not a nice sort of whole number. It's nice. Well, it's a fraction-y square rooty thing. So I know tan inverse is like 1 on a, where that's a squared. So square root of g on k. And that's tan inverse of v on a. And that equals to minus kt plus my third constant for integration. So before I actually before I sub in my initial conditions, maybe clean these two fractions up a bit. Just looks a bit scary right now. So that becomes like root k on root g tan inverse root k v on root g. So minus kt, here we are. Okay, we're ready to sub in our constant. So how much vertical space I have? Quite a lot actually. So when t equals 0, unfortunately the velocity is not 0, otherwise my life would be a lot easier. That guy there is, so that's gone. This guy here is just u sign, so I can clearly see that c3 equals to root k root g tan inverse of root k times u sine theta all over root g. So I'm going to sub this guy in. Now, this is where it gets a bit painful, but at the same time, I get quite excited when I do this because it's a bit tedious, but the answer itself comes out to be, well, actually not nice, but something that is, well, doable. So let's say minus kt, put the constant in here. Gee whiz, that is an ugly sight. Yeah, I guess this is why it's in 4 unit, because it is tedious. And all right, so let me just make sure I'm on the right track, because heaven forbid that I do some algebraic boo-boo and end up in a very painful place later on. So looks right, looks sweet. So what am I trying to do now, right? What's my aim? I need to make this a subject. So it feels like I'm going to times, or at least divide everything by this. Now, when I divide everything by this guy goes away, this guy goes away. And for this term, if you can imagine, times the root g up, divide the root k down. So if I sort of multiply this guy by root g on root k, the root k's cancel out and it becomes like times root k. So negative root, maybe both of them under the same square root of gk t to something that looks like this. So tan inverse of root k on root g of v equals to now. That becomes minus root GKT plus tan inverse of root K times u sine theta on root G. All right. Now, how do I get rid of the tan inverse? Yep. So obviously we're going to access, to get rid of tan inverse, I'm going to tan both sides because tan of tan inverse of x gives me back my original, right? Because they're mutually inverse. So you can imagine I'm going to be tanning this side and then tan of like this expression with this expression where one's minus, one's plus. It feels like I'm gonna, I'll move this up a bit. Feels like I'm gonna access the tan compound angle of A minus B, where we know that's gonna be tan A minus tan B over 1 plus tan A times tan B, right? So that's the compound angle we're gonna access on the right-hand side. Let's go there. So on the left, tan of tan inverse, we get that. On the right, compound angles. Woohoo, okay, let's see. This is going to be not pretty. So let me see what I got here. I got root K, T, also T rather, it's Y dot on root G, right? When I tan inverse. On the right, it's gonna be, now let's see, I'm tanning the tan inverse first because that's the positive element. So it's going to give me root GU sine theta. Let me just scroll down just to make sure. I'll just zoom out for a bit. So K, root K sine theta. Oh, K's on top. Be careful though. Careful. So let me just make sure I don't do that wrong. That was a K there. Yeah, on root G minus tan inverse of this expression here with a negative. Oh, that's certainly interesting. Oh, no negative because I put a minus there. Beautiful. That's root GKT all over 1 plus this expression. Multiplied by this expression. Oh, not tan inverse, right? Just tan. Just tan. Yep, that's the whole point of me just tanning it. You can see I'm already making a few sort of silly errors, but it's a good thing I know where I'm headed. That's the next step. Now, what am I trying to do, guys? I need to make this guy a subject. I need to remove this element. So times both sides by root G on root K. That guy goes away, that guy goes away, and this becomes root G on root K, right? Now, that's only on the numerator, right? Remember, algebraically, if it's a fraction, only times by the numerator. Yeah? So then I get an expression right now. I actually have an expression for y, and I just look, I'm looking at the future here. There's no fractions on top and bottom. So it feels like then once I write this down, I am going to common denominator or do something to get rid of all fractions to the top and bottom. And I'm almost there, actually. I'm almost there, right? Almost there. So this guy here becomes root K on root G, u sine theta tan. Now, like I said, right, look how monstrous this is. I get that. Now you can see the thing I need to prove has root GK's here, and right now it's a 1 and nothing there. So it feels like the logical step is to times top and bottom by root GK, times that by root GK, and I should get it. Let's see, root GK there, yes. Root K, you get G, yes. Root G, and you get perfect. And I have it. Well, I get the expression that I want, root GK u sine theta minus G. Oh, my tan inverse, my tan disappeared. So I'm just gonna borrow that, put my tan back in, and that guy there was root G on root K. G tan root GK, right? It's always good to know what you want, because then you know when you've made a silly mistake. So that should be the numerator on top, perfect. And on the bottom, it's root gk plus the root g's go away. It's just ku sine theta tan of root gkt. All right, give yourself a pat on the back if you're following that. Yep, because that was a little bit intense. Yeah, so, but that's only half the story, because that is just all y dot all velocity, right? We now want to integrate this monster again to get the displacement. And it's this part here that I really like, actually, because it's a bit crazy, you know, just a little bit crazy. So check this out. I'm gonna borrow, or you know, you don't even need that. I'm just gonna take this guy, plug it here. Just gonna copy it down here so I have another slide for an example later. All right, we are going to start with velocity and then try to integrate this. Now, what I'm gonna do to make my life and your life a bit easier, because I know this guy is everywhere and it's constant, I'm gonna let alpha equal to root gk. It just makes life a little bit easier. It's a constant. So once you do that, you get y dot equals to alpha times u sine theta minus g tan alpha t all over alpha plus ku sine theta tan alpha t. All right. Here we go. I'm going to do two things here. Step one, I'm gonna replace this with d dt. And then at the same time, I'm going to replace tan with sine and cos. All right, so we replace that with sine. Yep. So I get this. Let's see. All right. Common denominator. So get rid of your fractions, and you sort of get like this guy to be. Now let me see. Do I chuck it over? I don't need to. I'll chuck it over later. Maybe I'll just put an equal sign here just to save myself. I was going to chuck over the dt and then integrate both sides, but I'll do that later. So it's common denominator at the top. So you sort of get like cos theta t, whereby the top you'll get alpha u sine theta cos alpha t minus, didn't need to extend that much, sine alpha t. So I'm going to just quickly, yes. And the bottom you do the same, so common denominator again, cos alpha t. It's good because I'll cancel that out in a second. It's alpha cos alpha t plus ku sine theta sine. All right, here we go. We're going to do some manipulation magic. Obviously, this guy goes away. Yep. And we have top on bottom, almost there for what I want. Let me see before I do that. Now, this is what I'm going to do. Do you guys remember this formula, right? So from the reference paper, I'm going to try to integrate this, but if I have a fraction on the bottom, if I can get its derivative on top, right, that becomes ln of fx plus c, right? That's what I want to mimic, because right now the fx is this monster. Now, if that's the monster, so if I said this guy here was fx, what is f dash x? If I differentiate on that, I'm going to get sine the derivative, but I'll get negative alpha squared sine alpha t plus, you know, what's he? The is this guy here, so alpha goes in front, so it'll be k alpha u sine theta, everything's constant, cos alpha t. Now, why am I telling you that? Because I'm going to try to manipulate the top to look like this. Now, what's missing? Let's see if I can actually get it quite close. So there's a G in there. Not a fan of having the G in there, but check this out. G, now don't I have an expression for, yeah, there it is, right? So if I sort of made G the subject here, G square both sides, alpha squared divided by K will be alpha squared on K. I'm going to sub this into G. So it becomes like alpha squared on K. That's good because see how that's alpha squared there? It was on K. If I sort of then say to myself, alpha, alpha, u sine cos, if I sort of take out the K on the bottom, I actually get this. I'll show you what I mean. Let's plug this in here as the next step. So check this out. So the denominator looks like this, right? It's a really nice expression, guys, where it just so happens, right? It just so happens that to get this on the bottom, the derivative is actually very close. So if I just write the green, oops, as it is, with the exception of subbing in the value for G, so minus instead of G, put in alpha squared on K, sine alpha t. Look at this. The moment I factorize a K out, there's a K that needs to be forced here. That gives me this expression, right? It's almost there, right? It's just missing the K. And the moment I factorize a K out, I get this expression. In other words, on top, you have the derivative. The only difference is I need a 1 on K out, and I'm done. So what I'm going to do now is, because this equals to dv dt, not even dx or dy, I believe. Let me get rid of that dot. So then, therefore, if I sort of integrated both sides, get rid of this, put the dt here, force factorize the 1 on K out from the top, I have an expression that looks like this, where it's 1 on K, integrate. Now force factorize the K out, I get K. Now I'm going to need to zoom in here. I need to write quite small on here. Let's see. K alpha u sine cos minus, K's gone, forced it out, alpha squared sine alpha t. Have a quick gander to see whether that looks like a derivative, minus plus, perfect. Divided by the blue line here, which is the function itself, plus rather ku sine dt. I have it, right? That is lnable, if that's a word. Therefore, that equals to 1 on K. ln of this bottom denominator. And I'm sort of not done because I haven't found my constant yet. But hopefully, when I do sub in my constant, this ln will be 1. So plus C4. You can see, right? When t equals 0, subbing my initial conditions, and y rather, equals 0. So when this guy and this guy, when t is 0, cos 0 is, what's cos 0? 1? Cos 0 is 1. Sine 0 is 0. That's ln alpha. Ooh. ln alpha, is that what I want? Yeah. I want ln alpha because then I want the alphas to go away. Is that right? I'm going to have a quick look. Yeah, it is ln alpha. Yeah. Because then I do subtraction of ln and it goes like, beautiful. Wow, I'm not even done. So can I ask a favor? I'm just going to move this, park it down there, because I'm going to need a lot of vertical space to do this. All right, let's see. So when that's 0, that's 1. So I sort of get like C4, not 0, which is painful, but C4 equals to negative 1 on K ln alpha, right? It's actually not 0. So therefore, man, I thought I was done, but I'm not. Y equals to 1 on K ln of the thing that I proved downstairs, which was alpha cos, I'm just copying this blue over here, plus Ku sine theta sine alpha t, and then minus 1 on K ln alpha. Now, let me have a quick look at what I need to prove. Yep, see how there's alpha on the bottom, so perfect. Looks like what I'm going to do, combine the, and it's 1 on K positive, perfect. Combine the logs, 1 on K ln. You can see when the alpha divides by this, the alpha goes away. I'm just basically go alpha cos alpha t plus, so I'm just going to copy this guy, text for text, all over alpha. Alpha goes away, and then I'm going to sub alpha back in. What was alpha? Alpha was this. Back in, and I should have that expression. Let's have a look. Perfect, and then they broke it up as well. Makes it easier. Therefore, y equals to 1 on K ln. Alpha goes away, that's just cos. Replace alpha back in. T plus alpha sub root gk u sine root gk. My God, what a monster. Yeah, did I not tell you? Did I not warn you that that was going to be a beast? All right, there it is. The proof for the 6 equations of motion for resistance, that is velocity proportional to the square of velocity. All right. Okay, let's do a question, right? The questions themselves are not too bad, right? The questions themselves are not too bad, whereby I've prepared one a bit earlier, and it looks a little bit like this, right? It's just the proofs itself, right? So hopefully for this one, what I'm going to do to make your and my job easier, I don't say anything, you know, I don't ask you to prove the formulae. Some questions might. Let's just use them, right? So I'm just going to quickly go back to the formulas, and then I'm just going to paste them in here as formulas we're just going to use for this question. Now, you can sort of see in this question, right? Once again, let's comb through the English and extract out the juicy mass, right? So a projectile of mass, velocity, angle, experiences resistance, take it v squared, right? And last but not least, you got gravity, right? So, but resistance there is important. So the question itself asks for max height, horizontal range. So obviously max height when y dot equals 0. Horizontal range feels like I'm going to need to sub in y equals 0 to find total time of flight, and then sub that into x, right? That's the plan. Whew. Okay, let's have a go at this. So for the first part, right, I need to I need to ascertain what y dot is, right? So it feels like I'm going to access this formula over here. Yep. So then y dot equals to let's sub everything in. So that's like root gravity times what's the constant? The constant is the number, because that is kv, or it's actually mkv squared, right? Yeah, mkv squared. So that equals to 0.2 times by k times v squared. So that equals to v squared on 50, just to get the answer for k. So v squared obviously go like k is 50. What's that, 1 on 5? It's 1 on 10, isn't it? Or 0.1. Yeah, 0.1. So 0.1 there, which is nice because root 10 times 0.1 is root 1. So just to get that into your system, right, that you have to find the value of k to sub in to these values. So got in KU is obviously 20, sine 30, beautiful, that's a half. So everything is going well in terms of the exact values of these numbers. So that's 10, root 10 times 0.1 again, t, bracket, all over root 10 times 0.1 plus, now KU, so K is 0.1 times U, which is 20, sine 30, 10 of this guy again. Yep. Now, let's see what it cleans up to. So hopefully that's 1, 20, that's a half, that's 10, minus 10, 10t, that's 1, plus 10, that's 1, yep, 10t. Ooh, that brushes up quite nicely, that expression. So once you get that expression, I mean, what are you trying to do? You're trying to find a max height. So sub that, so let that equal to 0. And I'm going to need to solve this equation. So it's a tricky equation. So times that up, you try and find the time when it occurs. So it looks like 10 equals to 1, is it? So t equals to, well, pi on 4, 3 pi on 4, etc., etc. So maybe just use the first time it achieves that. It achieves that situation. So when t equals to pi on 4, sub that into the y value, right? Y equals to, so even then, look at this monster, right? I need to sub it into there on my calculator. So it'd be like 1 on k, so 1 on 0.1, which is 10, ln cos root 10 times 0.1, which is 1, times pi on 4 plus k times 20 sine 30 all over root 10 times 0.1. Got no horizontal space, so let me just shift this over a bit, and then sine root 10 times 0.1 t. Yep. So that cleans up to 10. You have to just clean it up a little. That's like cos pi on 4, right? Which is 1 over root 2 plus, what's that? That's 10. That's 1 on 1. That's 1. And times sine. Oh, not t. Not t though. That should be pi on 4. That's 1 over 2 as well. Is that right? Looks really nice. Looks really nice. Yeah, it is right. So you punch it in the calculator, and you should get 3.5 meters. And that's it. So it actually works out quite nice in terms of the values. Yeah. Admittedly, the numbers chosen for this question are specifically chosen to give you a really nice rounded answer. It's not always the case. So what I'm going to do is do part B now. Now part B, a little bit more involved, and I like it in terms of where it's headed in terms of how you go about doing it, because you need to use a bit of transformation. Oops, deleted the question. All right. So in part B, we are no longer using that. We're using the horizontal range. So like I did before, what that implies horizontal range is that I set y equals 0, solve for time, and then sub that into the x value, right? So let's do that. So I need to solve this guy equal to 0. Jeez. All right. So let's see. So for part B, when y equal to 0, that's 1 on k ln cos, also let's not do k, right? We know k, that's 0.1. Sub everything in cos. Can I shortcut this to just 1 root 1 t plus, what's that? I think I did it before. Let's just go to it. You know what, guys? Let's just go to it. Let's just be awesome. 10 cos t plus sine t, and that equals 0. Obviously, the 10 goes away. 10 goes away, and I have ln. That goes away. Exponential both sides, and you get cos t plus sine t equals to 1, which is a nice sort of transformational t results question. So if you let this be transformation, right, that would be like r cos t plus alpha equals to 1. Yep, do your thing, where if you expanded that, you get r cos t cos alpha plus minus, no, yes, that needs to be a minus there because it's cos, plus r sine t sine alpha equals to 1, therefore comparing, not even comparing, 1, no, just this guy, and then comparing this guy to the 1 and the 1 here, so I got r cos alpha equals to 1, r sine equals to 1, cos alpha equals to 1 on r. Now, I already know the numbers, but, you know, for your case, right, just for full complete sort of working out, that's root 2, therefore r is root 2, and that is pi on 4. All right, that was fun. So this guy transforms into root 2 cos t minus pi on 4 equals to 1. Is that right? Perfect. So using my all stations central, divide the root 2 over, I get t and then cos that. What's that? 1 over root 2 is pi on 4. And then because it's cos, right, doesn't know about the other one, so let's just solve it for the first instance. That's when maximum range occurs. So sub that into the x value and you should be able to do it. So do I have much space? Yes. Therefore, x equals 2, right? What's my formula for x? It's not too bad. So 1 on 0.1 ln of k times 20 times sine 30 degrees times pi on 2 plus 1. That's like 10 ln. That's all 1, I believe. That's just pi on 2 plus 1. Punch in the calculator. I believe it's x equals to 13.1 meters. All right. Wow. Okay. Well done. So the questions themselves generally are much easier in that sometimes much easier because they don't ask you to prove the formulas. Well, not yet anyway, not from what I've seen in the trial papers. But if you ever come across a question that has the proofs, then it's going to be a bit tedious, but just be really careful about your integration. It'd be a wise idea to basically brush up on it because there is that tricky substitution for alpha, etc. So the proof itself, completely tedious, very long-winded, but that's how you do it. So hopefully that video was useful. Once again, if you liked that video, please click on that like button and give me a subscribe and tell your friends. Next lesson, we will be doing past paper questions and basically wrapping up the whole topic and putting it all together. So I'll see you guys then. Thank you.